right, we have a couple of different topics that we want to hit today. One is some of the effects of van der Waals forces on behaviors, and the other is going to be phase diagrams. Van der Waals forces is what we'll hit first, and van der Waals forces can result in three different effects. The first effect is called cohesion, and that's when you have forces between the molecules of a substance. Okay, so therefore you've got molecules that are going to cling to each other. That's what van der Waals forces are all about anyway, right? They cling to each other. And he specifically mentions viscosity. Viscosity is a liquid's resistance to flow. So if you think about something like oil, and you compare that to water, obviously oil is going to flow a lot less easily than water will. If you think of something like honey, honey does not flow very quickly. Maple syrup does not flow nearly as quickly as water does. And so all of those things have a higher viscosity, and it's because the molecules of the liquid are attracting each other, and so they don't want to flow. Viscosity is always going to go down as you increase the temperature. And so you can remember that probably by, if you've ever had honey that turns to sugar in your container, you know that you can turn it back into the liquid form by heating it up. When you do that, though, your honey tends to get very, very runny while it's still hot. It will thicken back up again as it cools down, but as you raise the temperature, the viscosity is going to go down. And he mentions why that's so important in a car, to let your car warm up on a cold day, so that the oil in the car is actually running well, so that it can lubricate the engine. And if you start too soon, then it doesn't have that lubricating ability because it doesn't flow very well. Okay. Surface tension is also a result of cohesion, and we talked quite a bit about surface tension in the last video, so I'm not going to go into a lot of detail about that here, but it is definitely true that the more polar your molecules in your liquids, the greater the surface tension they're going to have. Okay, so cohesion. You can also have adhesion, and adhesion is when you've got forces between the molecules of a liquid and the surface that it's on. I know my biology students have just recently done an experiment where they were piling water onto a coin or onto wax paper, and how it beads up as opposed to just going splat all over the place. And it's because the molecules are adhering to each other. So that's the cohesion. But when you put it in a graduated cylinder, you should recall that when you've got your liquid in there, it's going to go up like that. And so when you read your graduated cylinder, you have to remember that you always read it from the bottom, that this is where you need to look when you're reading your graduated cylinder, from the bottom of the meniscus and not from the top. And that adhesion is because this meniscus is because you've got molecules that are clinging to the glass, and that's what's going to cause that meniscus. And not every liquid is going to cause a meniscus like this. It depends on the nature of the liquid, and you'll see that. I believe it was in on your own questions. You'll see that. All right. There's another type of effect that happens when these two, when cohesion and adhesion are almost competing with each other, and that's called capillary action. And this one is not in your book, so you probably will want to write this down. Okay, capillary action is when you have a spontaneous rising of a liquid through a narrow tube against gravity. Now, if you have already taken biology, which I would hope by this point that you've already had biology, we talked about capillary action when we talked about the xylem in a plant, and how the plant is able to pull water up from the roots all the way up to the tips of its leaves through capillary action. And so what happens there is that you've got water evaporating from the leaves as they're opening their stoma during the day. And so you've got your water then that it's got a negative pressure because some of the water is evaporated. And so in an effort to equalize the pressure, the water is going to move up against gravity. It also is going to cling to the xylem, and it's going to cling to each other, and it's going to continually be pulled up the xylem so that the plant can get all of the water that it needs all the way to the tips of the leaves. Okay, so if you recall that discussion from biology, that's what capillary action is. You can also see it in a chemistry lab. If any of you are going to go on to take chemistry in college, which I imagine probably a lot of you, if you're taking this course, that's probably where a lot of you are headed. If you use some really, really thin, narrow glass tubing, you will see the effects of capillary action in a situation like that as well. All right. I want to talk about phase diagrams because a phase diagram is absolutely crucial for you to understand how to read it and how it works, okay? In a phase diagram, you're going to have different phase diagram for every substance. We've got pressure, increasing pressure on the y-axis, increasing temperature on the x-axis. And the shape is always going to have this very general shape. It's going to be different, obviously, from one substance to another, but this is going to be the same general shape. And in general, what you're going to see is that this is going to be the area where the solid is, this is going to be the area where the liquid is, and this is going to be the area where the gas is, okay? Now, what is the deal with these lines? Well, as we have already talked about, temperature and pressure both affect where a liquid evaporates, where it boils, where it melts. And so the line right here, this is going to be the line in this section up here from this side of the line to this side. This is where melting is going to take place. And if I go from this direction to this direction, this is where freezing is going to take place, okay? So melting going this direction, freezing going this direction, okay? So what this line indicates then is your melting point. From here to here, and not down here, once you start right here. So this is your melting point, okay? Down here, this is where it is possible for sublimation to occur, where I can go from a solid directly to a gas. Now, you may have seen sublimation if you've ever had any contact with dry ice, because if you've got a chunk of frozen carbon dioxide and you just let it sit out, it just starts, it looks like it's steaming or smoking. That's really not what it is. It's actually vaporizing. You've also probably seen this if you have ice in your freezer and you have ice cubes that maybe get caught way in the back, like if you have an ice maker and it flings the ice all the way to the back of the freezer and then they get lost back there, or if you've lost an ice cube and it falls down to the bottom of the freezer and then you pull it out later and you find that those ice cubes are way smaller than the other ice cubes were. Well, obviously they've not melted because it's too cold in the freezer for that to happen. They're not going to melt, but they have sublimed. They have turned into vapor while they've been in the freezer, and they've gotten smaller. Okay, so from here to here, this is the process of sublimation. And then when I go the other way, that is called deposition. Okay, the opposite of sublimation. And so from this point to this point, that is going to be the vapor pressure that it's going to be at which that substance is actually going to vaporize. Now, I've got one section of line that I've not talked about, and that's from here to here. One other thing, you'll notice that this line is relatively vertical, and it's going to be that way on almost all of your phase diagrams because pressure does not greatly affect the melting temperature of a substance. Okay, so that's why this is going to be almost all vertical. Okay, so now I've got this particular part. Obviously then this is going to be from here to here. This is going to be vaporization. And going from here to here is when I'm going to have condensation. Okay, so this line is going to tell me, it's also going to tell me vapor pressure, but it's also going to tell me the boiling point of the substance. And you will see that there is a much greater difference here than there is here because pressure has a much higher effect on the boiling point of a substance. Okay, what is this thing right here? Well, that point where all three phases can exist simultaneously, this is called the critical point. I'm sorry, not the critical point. That's called the triple point. I'm getting ahead of myself. So this is the triple point where all three substances can coexist at the same temperature and at the same pressure. Okay. The critical point is actually up here. Sorry, I misspoke there. So this is the critical point. And the critical point of a substance is the point at which no matter how much more pressure you apply, you cannot turn the gas back into a liquid again. It's just not possible, okay? So the critical point, once again, is the point where you can no longer turn the gas back into a liquid no matter how much you increase the pressure, okay? You're gonna have to, if the temperature stays the same, it's not gonna go back the other way. All right, so that is all the nitty gritty of phase diagrams. I don't think there's anything there that I forgot to tell you. Yeah. So beyond the critical point, you can't distinguish the gas and the liquid from each other. There was one more example that I did want to give you when we were talking about hydrogen bonding. If you look at two substances, CH3OH and CH3OCH3, okay? If I look at those and I want to ask myself, which one of these has the higher vapor pressure and which one has the higher boiling point? We talked about hydrogen bonding before, but I wanted to show you something that looks like this because I didn't want you to mistake something that has hydrogen bonding for something that does not. This compound is going to look like this. Here's my CH3, like I showed you the other day, and it's going to have an oxygen and a hydrogen. So because this hydrogen is directly bonded to the oxygen, this compound is going to exhibit hydrogen bonding, okay? Now, this compound looks like this. It's got a carbon with 3 hydrogens attached to it, CH3, that's bonded to an oxygen, that's then bonded to another carbon that has 3 hydrogens attached to it, okay? Does this have a hydrogen bond? If you remember the definition of a hydrogen bond, the hydrogen, if you're gonna have hydrogen bonding take place, the hydrogen has to be bonded to an oxygen, a fluorine, or a nitrogen. Well, in this case, the oxygen isn't bonded directly to the hydrogen, so this compound does not have hydrogen bonding, even though there is an oxygen in it. This one is going to be dipole-dipole. It's going to be able to have some polar molecules. It's going to have some positive and negative charges in it. It's pretty symmetrical. So the effects of the polar molecule, I mean, if you looked at this, you'd probably say, there's really not much of a polar molecule there because it is so symmetrical, but there could be some dipoles in here just because of electronegativity differences. Therefore, since this one exhibits hydrogen bonding and this one does not, which one then is going to have the higher boiling point? Well, hopefully you said that this one, because it has hydrogen bonding, this one is going to have the higher boiling point because it's harder for those hydrogen bonds to be broken. The higher the boiling point, the lower the vapor pressure, and so therefore this one is going to have the higher vapor pressure. Okay, so I wanted to make sure I showed you that example so that you weren't under the mistaken impression that just because there's an oxygen present in something that has a hydrogen, that there would automatically be a hydrogen bond, because it depends where that oxygen is going to be located. So I wanted to point that out to you. All right.